A galaxy exists where light itself is swallowed whole. This is not science fiction. It is a dark galaxy, one of the most elusive and ancient structures in the cosmos. These are not merely empty voids, but massive, ghostly islands where the normal rules of the universe seem to break down, dominated by a mysterious substance we cannot see. By the end of this journey, you will know the 25 most terrifying dark galaxies that challenge everything we think we know about reality. We will visit a cosmic ghost with the mass of our Milky Way, yet almost no light, and a dwarf galaxy that might be tearing itself apart from the inside with dark matter. What do you fear most about the unseen universe? The first name on our list is Dragonfly 44, and it redefines the meaning of a cosmic ghost. Nestled within the dense Coma cluster, this galaxy is a whisper against a roaring background. If you could place it side by side with our own Milky Way, the difference would be shocking. They possess roughly the same staggering mass, but where the Milky Way blazes with the light of hundreds of billions of stars, Dragonfly 44 emits a mere 1% of that brilliance. It is an ultra-diffuse galaxy, a vast, wispy cloud of stellar fog so faint it was only spotted with a specially designed telescope array, one named for the insect with the most sensitive eyes. The immediate question was terrifying in its simplicity. Where did all the mass go? The answer is that it never left. It was just never visible to begin with. Calculations revealed the unsettling truth. Dragonfly 44 is not missing its mass, it is drowning in it. An astonishing 99.99% of this galaxy is made of dark matter. Think of it like a city the size of New York, but where only a single, flickering street lamp is lit. Everything else, the skyscrapers, the streets, the very ground beneath your feet, is utterly invisible and incomprehensibly heavy. This is not a galaxy with some dark matter. This is a dark matter halo that, almost as an afterthought, contains a few scattered stars. Its discovery sent a chill through the astronomy community because it proved such extreme objects were not just theoretical nightmares, they were real and they were hiding in plain sight. Dragonfly 44 stands as a monument to our ignorance, a ghostly leviathan whose true nature remains locked in the dark. But what if the opposite were true? What if you found a galaxy that seemed to have no ghost at all? That is the profound and terrifying puzzle of the second dark galaxy, NGC 1052 DF2. While Dragonfly 44 is a dark matter fortress, this galaxy appears to be a castle built on sand, a structure that by all rights should not exist. It is a similar ultra-diffuse ghost, a wispy collection of stars, but when scientists measured the motion of its bright globular clusters, they got a result that sent shockwaves through cosmology. Those clusters were moving slowly, far too slowly. In a normal galaxy brimming with dark matter, the immense invisible mass whips stars and clusters into a frenzied orbit. Here, the measured motion could be explained by the gravity of the visible stars alone. The conclusion was staggering. NGC 1052 DF2 seemed to possess little to no dark matter. This was not just surprising, it was a direct challenge to the very bedrock of modern astrophysics. Our entire understanding of how galaxies form is built upon the scaffolding of dark matter halos. They are the gravitational seeds that first gathered ordinary matter, the cosmic frameworks upon which the luminous universe is painted. A galaxy without dark matter is like a skyscraper without a steel frame, a sandcastle that somehow reached the clouds. The immediate reaction from the scientific community was a mixture of fascination and deep skepticism. Could the measurements be wrong? Perhaps the distance to the galaxy was miscalculated, throwing off all the mass estimates. Or maybe the globular clusters were not true tracers of the galaxy's gravity. The debate raged, with papers published and refuted in a tense back and forth. The fear was not about the galaxy itself, but about what it meant for our models. If it were real, it implied that galaxy formation was far more complex and chaotic than we thought, that luminous matter could somehow clump together without the dark matter anchor. It suggested there might be pathways to building a universe we do not yet comprehend, or worse, that our fundamental assumptions about gravity itself were flawed. The existence of a galaxy devoid of dark matter is in many ways more frightening than one made almost entirely of it. It does not just hide a mystery, it threatens to dismantle the map we use to navigate the cosmos. The search for dark galaxies was not confined to distant clusters. It led astronomers to look closer to home, and what they found hiding in our own galactic neighborhood was profoundly unsettling. Drifting through the halo of the Milky Way is Antlia 2, a galactic ghost of staggering proportions and shocking faintness. This dwarf galaxy is enormous for its class, spanning nearly one-third the width of our own Milky Way's luminous disk. Yet it emits so little light that it remained completely invisible to every survey until just a few years ago. Its surface brightness is so low that if you could stand on a planet within it, the night sky would be almost pitch black, with only a handful of lonely stars punctuating the emptiness. It is less a collection of stars and more a wisp of stellar smoke, a phantom limb of our own galaxy. The fear its discovery sparked was immediate and deeply personal. How could something so large orbiting our own home have stayed hidden for so long? The answer is a lesson in cosmic camouflage. Antlia 2 is not just faint, it is perfectly diffuse. Its scant stars are spread over such a vast area that they blend seamlessly into the foreground clutter of our own Milky Way starfield. It was only the precise motion data from the Gaia satellite, which mapped the movements of billions of stars, that betrayed its presence. By tracking stars moving in concert, astronomers finally pulled back the curtain on this ghost. This leads to the chilling implication that haunts every astronomer studying the dark universe. If Antlia 2, a giant hiding in our backyard, could evade detection until now, how many more are out there? Our galaxy's halo could be swarming with similar dark, diffuse satellites, each a massive reservoir of dark matter orbiting unseen. Every patch of seemingly empty sky might be concealing a phantom galaxy, its gravitational pull subtly influencing the Milky Way in ways we do not yet understand. The cosmos may be far more crowded with ghosts than we ever dared to imagine. Yet the most extreme examples of darkness are often the smallest. Orbiting our galaxy like a faint, forgotten moon is an object that holds a record which chills astrophysicists to the core. This is Segway 1, a dwarf galaxy so insignificant in light that it was once mistaken for a simple star cluster. It contains only a few hundred ancient, dim stars, a population smaller than some globular clusters. But this tiny flicker of luminosity tells a monstrous lie. When astronomers measured the motions of those few stars, they were stunned. The stars were whipping around at velocities that should have torn the entire structure apart. The only force powerful enough to hold them together was the gravity of an immense, invisible mass. The numbers are almost incomprehensible. Segway 1 is roughly 1,000 times more massive in dark matter than it is in ordinary star-forming stuff. For every single speck of luminous matter you can see, there are 1,000 specks of the unseen. This makes it arguably the darkest galaxy ever discovered, the champion of dark matter domination. The fear surrounding Segway 1 is not just about its composition, but about its origin. What is this thing? One terrifying possibility is that it is a failed galaxy, a cosmic stillbirth. In the early universe, a small pocket of dark matter may have begun to gather gas, but something went wrong. Perhaps it was stripped bare by a larger neighbor, or it formed in such a barren region that it never collected enough fuel to ignite widespread star formation. It is a ghost of what could have been, a skeleton of a galaxy that never truly lived. The other, even more profound possibility is that Segway 1 is a pristine relic. It may be a fragment of the primordial universe that has survived almost unchanged for over 13 billion years, a frozen snapshot of conditions just after the Big Bang. Its stars are incredibly metal-poor, meaning they are made almost entirely of hydrogen and helium, the original elements. This suggests it may have formed from gas that was never enriched by the deaths of earlier stars. If true, studying it is like finding a perfectly preserved fossil from the dawn of time, one that could reveal the purest properties of dark matter itself. This tiny, faint smudge on the edge of our galaxy is not an afterthought. It is a vault, and within it may be locked the original blueprints of the cosmos, written in a language of darkness we are still struggling to read. The pristine darkness of Segway 1 presents one kind of fear, the fear of a silent, ancient vault. But there is another galaxy, a different kind of phantom, that hints at a far more violent end for the unseen universe. Lurking in the constellation of Triangulum is an ultra-faint dwarf named simply Triangulum 2. It is another ghostly wisp of stars, but this one may hold a lethal secret at its heart. Astronomers studying data from the Fermi Gamma Ray Space Telescope noticed something extraordinary, a faint but persistent spike of high-energy gamma rays emanating from the precise direction of this tiny galaxy. Gamma rays are the most energetic form of light in the universe, often produced by the most violent events imaginable, like colliding black holes or exploding stars. Yet Triangulum 2 is quiet, old and inert, with none of the usual stellar engines to create such a signal. So what is generating this deadly radiation? The most thrilling and terrifying hypothesis is that we are witnessing dark matter commit suicide. Here is the theory. If dark matter is made of a certain class of theoretical particles, like weakly interacting massive particles, then these particles could be their own antimatter counterparts. When two of them collide under the immense gravitational pressure at the dense core of a galaxy, they would annihilate each other in a flash of pure energy, producing the very gamma rays we detect. Triangulum 2, with its high concentration of dark matter and lack of competing astrophysical noise, could be the perfect, quiet laboratory to see this self-destruction in action. The fear and excitement this generates is palpable. On one hand, it is the stuff of scientific dreams, the first direct, tangible signal of dark matter's fundamental nature, caught in the act of its own demise. It would be a discovery that reshapes physics. On the other hand, the implications are deeply unsettling. It paints a picture of dark matter not as a passive, eternal scaffold, but as an active, dynamic substance engaged in a constant, invisible war within itself. The cores of dark galaxies could be cosmic battlefields where particles we cannot see are constantly obliterating each other, flooding space with silent, lethal radiation. If this is true for Triangulum 2, then it is likely happening in every dark matter halo, including the one that envelops our own Milky Way. We are living inside an invisible furnace, a galaxy whose true power source is the mutual annihilation of ghosts. The signal from Triangulum 2 remains tantalizing but unconfirmed, a whisper in the gamma ray static that could be the key to everything or merely a cosmic mirage. But it forces us to confront a new possibility that the darkness holding the universe together is also slowly burning itself away. The silent annihilation within Triangulum 2 speaks of an invisible war, but some dark galaxies bear scars from a conflict we can see. Just beyond the familiar spiral arms of our Milky Way lies a phantom of a different kind, one stretched and smeared by a gravitational violence we are only beginning to understand. Its name is Crater 2, and it holds a paradoxical title. It is the fourth largest satellite galaxy orbiting our own, a behemoth in terms of sheer physical size, yet it is one of the faintest objects ever discovered in the sky. If you could see it with the naked eye, it would appear as a vast, ethereal smudge, a pale ghost of light twice as wide as the full moon, but with a surface brightness so low it was lost in the stellar glow for decades. The sheer fact we can detect it is a marvel of modern astronomy. Its stars are not clustered tightly like a typical galaxy. They are spread out with an almost impossible thinness, like a handful of glitter tossed across a football field. This puffed-up, diffuse state is the source of a profound fear for scientists. How does a galaxy become so fluffy? The leading and most dramatic explanation points to a history of cosmic assault. Astronomers theorize that Crater 2 was not always this faint and stretched. In the distant past, it may have been a more compact, normal dwarf galaxy. Then, on its long, looping orbit around the Milky Way, it ventured too close. Imagine a time-lapse simulation, not of stars colliding, but of space itself being warped. As Crater 2 swung by the immense gravitational well of our galaxy, it experienced a series of devastating tidal shocks. These are not waves in an ocean, but brutal stretches and compressions in the fabric of space-time. The Milky Way's gravity would have pulled harder on the near side of the dwarf than the far side, effectively trying to tear it apart. This process, repeated over billions of years, did not destroy Crater 2 completely. Instead, it robbed the dwarf of its dark matter and its most loosely bound stars, puffing the remaining galaxy up like a cosmic cotton ball, leaving it a pale, expanded shadow of its former self. It is a ghostly remnant of a battle it could never hope to win, a testament to the fact that our seemingly serene Milky Way is in fact a cannibal, slowly dissolving its smaller companions. Crater 2 is the evidence, a galactic casualty walking a slow, stretched-out path to oblivion. The fate of Crater 2 is not unique in our local group of galaxies. Orbiting our colossal neighbor, the Andromeda Galaxy, is a phantom that takes this dissolution to its absolute extreme. This is Andromeda 19, a structure so thoroughly stretched and unraveled that it barely earns the title of galaxy at all. What astronomers see through their telescopes is less a distinct object and more a faint, ethereal river of stars, a tidal stream adrift in Andromeda's immense gravitational pull. It is a smear of ancient light, a ghostly contrail marking the path of a dying system. The fear Andromeda 19 inspires is not about its composition, but about its destiny. It represents the final, gasping stages of a galaxy's life, a preview of a complete gravitational dismantling. This is what happens when a smaller galaxy ventures too close to a giant and loses a war of attrition over billions of years. Andromeda's gravity acts like a cosmic tide, pulling relentlessly at the dwarf, not with a single catastrophic rip, but with a patient, persistent tug that slowly draws out its stars into a long, faint stream. Eventually, Andromeda 19 will cease to be a coherent entity. Its stars will simply merge into the vast, diffuse halo of its captor, leaving no trace of its original form. This process forces us to look ahead to a collision written in the stars. In roughly 4.5 billion years, our own Milky Way and the Andromeda Galaxy are destined to merge in a slow, majestic dance. As the two titans intertwine, their immense gravitational forces will wreak havoc on their satellite systems. Smaller galaxies like our own Magellanic Clouds, and perhaps even faint dwarfs like Crater 2, could be stretched and shredded into tidal streams of their own. Andromeda 19 is a chilling prophecy, a glimpse of the violent orbital mechanics that will reshape our entire local neighborhood. It shows us that galaxies are not eternal islands, but temporary structures in a constant state of gravitational negotiation and sometimes total annihilation. The faint stream we see today is a tombstone marking not just the death of one galaxy, but foreshadowing the turbulent future of our own cosmic home. The faint stellar streams of Andromeda 19 show us a galaxy in its death throes, but what about one that was never truly born? Deep within the immense Virgo cluster, a gathering of thousands of galaxies, radio telescopes picked up a signal that sparked a decades-long cosmic mystery. This is Virgo HI-21, a cloud of cold, neutral hydrogen gas drifting through intergalactic space. When astronomers first mapped it, they saw a familiar signature, the telltale swirl and rotation of a galaxy's disk. But when they pointed their most powerful optical telescopes at the same exact coordinates, they saw nothing. No stars, no stellar nurseries, not a single pinpoint of light. Just the empty blackness of space. Here was a ghost with a voice but no body, a galactic skeleton of pure, starless gas. The immediate and terrifying question was simple: what are we looking at? The debate that followed tore at the very definition of a galaxy. One camp argued this was the Holy Grail, a true dark galaxy. A massive cloud of dark matter, they proposed, had gathered this primordial hydrogen, but due to some unknown quirk of physics, failed to ignite the spark of star formation. It would be a cosmic stillbirth, a monument to a universe where the most fundamental process of creation can simply stall. Imagine a cloud of gas and dust vast enough to form billions of stars, just sitting there in the eternal cold and dark, forever silent. This possibility is fundamentally frightening because it suggests our universe is littered with these failed attempts, dark matter halos that never lit up, forever haunting the voids between the stars. The other camp offered a more conventional, yet still violent, explanation. Perhaps Virgo HI-21 is not a galaxy at all, but tidal debris. In the crowded, chaotic core of the Virgo cluster, galaxies constantly brush past each other, their gravitational forces pulling out long streamers of gas. This object, they argued, could be a shredded remnant, a cosmic scrap of hydrogen torn from a larger galaxy during a close encounter, now drifting alone. It would be a ghost, yes, but a ghost of a past catastrophe, not a failed creation. The evidence remains tantalizingly ambiguous. The cloud's rotation suggests a coherent structure, a hint of the order seen in true galaxies. Yet its location in a dense cluster makes the tidal debris story equally plausible. For years, astronomers have scrutinized every pixel, searching for any faint glow of stars that would settle the debate, but the darkness holds its secret. Virgo HI-21 forces us to confront an unsettling limit of our knowledge. We can detect the raw material for stars, we can see the gravitational influence of dark matter, but we still cannot say for certain if this object is a building block that never assembled or a piece of one that was torn apart. It is a cosmic Rorschach test, and in its ambiguous shape, we see our deepest fears about the silent, unfinished corners of the universe. The possibility that Virgo HI-21 is just cosmic wreckage is, in its own way, just as unsettling as the dark galaxy theory. Astronomers studying the violent dynamics of galaxy clusters realized something profound. The chaos of these crowded places can create perfect illusions. Picture two majestic spiral galaxies, each containing hundreds of billions of stars drawn together by gravity. They do not collide head-on like billiard balls. Instead, they engage in a slow, gravitational dance that lasts hundreds of millions of years. As they swing past each other, their immense gravitational fields act like tidal forces on an oceanic scale, but they pull on the galaxy's own gas. This can yank out enormous ribbons of cold hydrogen, stretching them across thousands of light years into long, dark, and surprisingly coherent streams. These streams can rotate, they can hold their shape for eons, and from our distant vantage point, they can look exactly like a standalone galaxy, a ghost with no stars. This is the tidal debris theory, and for Virgo HI-21, it fits the environment perfectly. The object sits in the heart of the Virgo cluster, a celestial metropolis teeming with galaxies that are constantly interacting. It would be more unusual to not find such debris there. The fear this creates is not about a single object, but about the entire field of study. If something as promising as Virgo HI-21, with its rotating gas signature, could turn out to be a mere scrap from a galactic collision, then how many of our other dark galaxy candidates are also mirages? The hunt for these cosmic phantoms becomes a detective story where every clue is ambiguous. Is that faint wisp of hydrogen a primordial dark galaxy, or is it the shredded banner of a long-forgotten galactic war? The evidence we can gather from such distances is frustratingly limited. We can measure rotation, we can estimate mass, but without that crucial spark of starlight to confirm a true, self-contained system, we are often left guessing. This transforms the cosmos into a hall of mirrors, where the shadows of normal events perfectly mimic the forms we desperately seek. It means the universe might be even more clever at hiding its darkest secrets than we thought, using the violent aftermath of luminous collisions to disguise the true, silent failures we have yet to find. The line between a cosmic ghost and a cosmic cradle is thinner than we ever imagined. Within the same dense Coma cluster that hides Dragonfly 44, astronomers found another phantom, but this one held a faint, impossible spark of life. Its name is Coma P, an ultra-diffuse galaxy so faint it pushes the limits of detection, a wisp of stellar smoke against the black velvet of space. Yet when researchers analyzed its light, they discovered something that should not exist. Scattered within that ancient, ghostly haze were telltale signatures of young, blue stars. This galaxy, against all odds, is still giving birth. This discovery struck a chord of deep unease in the astrophysics community because Coma P is not just breaking one rule, it is shattering an entire rulebook. The first broken rule is about environment. The Coma cluster is a galactic metropolis, a crowded, violent city of thousands of galaxies whizzing past each other at tremendous speeds. The space between them is filled with a superheated plasma, a brutal intergalactic wind. For a small, fragile galaxy like Coma P, entering this environment should be a death sentence. As it plows through this searing gas, a process called ram pressure stripping should occur, violently tearing away its cold hydrogen fuel, the very raw material needed to make new stars. It is like a delicate dandelion seed being blasted by a hurricane. The galaxy should be stripped bare and left to fade, yet the young stars are there. The second broken rule is about density. Coma P is not just faint, it is fantastically diffuse. Its existing stars are spread so thinly that the gravitational pull they exert on each other is incredibly weak. In such a ghostly, low-density environment, the simple act of gathering enough gas to collapse under its own gravity and ignite a new star should be nearly impossible. Think of trying to start a campfire with a few scattered, damp twigs spread across an entire football field. The conditions are all wrong for a sustained flame. So how is Coma P doing it? The fear is that we are missing a fundamental piece of physics. One terrifying possibility is that Coma P is not a native of the cluster at all, but a recent visitor. Perhaps it is on its first fatal plunge into this chaotic realm, and we are catching it in a fleeting moment of grace, watching it form its last generation of stars just before the cluster's environment snuffs it out forever. Another, more profound idea is that its immense dark matter halo, the invisible scaffold that likely surrounds it, is playing a crucial role. This dark matter could be providing a protective gravitational cocoon, shielding pockets of its cold gas from the cluster's ravaging winds, or it could be creating dense enough knots within the galaxy to trigger localized star formation against all odds. Coma P is a paradox, a whisper that is also a nursery. It forces us to admit that galaxy evolution is not a simple, one-way street towards darkness or death. Even in the most hostile corners of the universe, in the faintest ghosts we can find, the stubborn, beautiful process of creation finds a way. And if it can happen there, in the last place we would ever look, what other rules are we wrong about? NGC 5846 UDG1 is a ghost with a secret past. This ultra-diffuse galaxy drifts through space as a faint, wispy cloud, a textbook example of a cosmic phantom. But when astronomers trained their telescopes on it, they noticed something that made no sense. Orbiting this faint smudge of light was not just one or two, but an entire swarm of globular clusters. These dense, spherical collections of ancient stars are typically the jewels of massive galaxies. Our own Milky Way, a giant spiral, has about 150 of them. For a galaxy as faint and diffuse as NGC 5846 UDG1, to possess so many is like finding a small, crumbling cottage guarded by a private army fit for a castle. The numbers tell a terrifying story. This ghost has a retinue. The immediate and chilling implication is that this galaxy is not what it seems. It is not a failed, quiet entity that never gathered much mass. It is a survivor, a cosmic corpse. The fear among scientists is that we are looking at the stripped-down skeleton of a galactic giant. Picture a then and now depiction. Billions of years ago, this object may have been a magnificent spiral or elliptical galaxy, perhaps 10 or even 100 times more massive and luminous than it is today. It would have blazed with the light of hundreds of billions of stars, its gravitational might holding a vast halo of dark matter and that immense family of globular clusters. Then catastrophe. Perhaps it ventured too close to the heart of its galaxy cluster, a dense and violent environment. There, it would have been subjected to a brutal process called tidal stripping. The relentless gravitational pull of the cluster's core and the countless close encounters with other giant galaxies would have acted like cosmic sandblasters. Over eons, these forces ripped away the galaxy's outer layers of stars, gas, and dark matter, leaving only its most tightly bound core and its hardy globular clusters, which orbit too closely to be easily stolen. The luminous, majestic galaxy was devoured, leaving behind only this pale, diffuse ghost and its swarm of loyal clusters as a tombstone. This transforms our understanding of these dark galaxies. They may not all be eternal phantoms. Some are the lingering echoes of a violent death. The cosmos might be filled with such galactic corpses, the remains of giants that once ruled their patches of space, now reduced to faint, haunting shadows. Their current state is a lie, a mask of tranquility over a history of unimaginable violence. Every ultra-diffuse galaxy we now discover, drifting so peacefully, could be hiding a past of cosmic cannibalism, a ghost story written in the stubborn loyalty of ancient star clusters. The hunt for these galactic ghosts required a new kind of vision, one that could see past the light entirely. This is where the Arecibo telescope, before its tragic collapse, made one of its most profound contributions through a project known as the Alfalfa Survey. Instead of searching for starlight, Arecibo's giant dish listened for the faint radio whispers of cold, neutral hydrogen gas, the primary fuel for star formation. It scanned vast swaths of the sky, mapping the invisible infrastructure of the cosmos. What it found was a gallery of phantoms. The survey catalogued dozens of objects with clear, rotating signatures of hydrogen gas, the unmistakable fingerprint of a galaxy's disk. But when optical telescopes followed up on these coordinates, a significant number revealed nothing but empty space. No stars, just the silent, swirling gas. These are the Alfalfa dark galaxy candidates, objects like Leo T, a faint dwarf with gas but almost no stars, and others known only by catalog numbers, their true nature still debated. The method itself is simple yet revolutionary. Find the fuel and you will find the galaxy, even if the galaxy itself refuses to light up. This leads to a fear that is both expansive and intimate. If a single survey covering only a portion of the sky could uncover so many candidates, then the true population of these dark objects must be staggering. We are not talking about a handful of cosmic oddities. We could be looking at a shadow universe, a vast, intermingled population of dark galaxies that exists alongside the luminous one, like ghosts living in the same houses as the living. They flow through the same voids, orbit the same clusters, and exert their gravitational pull on the bright galaxies we see, yet they remain almost entirely invisible to us. This hidden architecture could be the true backbone of the cosmic web, a dark framework upon which the glittering cities of stars are merely the decorative lights. The Alfalfa candidates are like hearing faint breaths in a dark room, confirming we are not alone, but leaving us blind to the number and nature of the beings sharing the space with us. It suggests our census of the universe, our entire map of reality, is missing perhaps the majority of its structures. We have been studying the skeleton by looking only at the jewelry draped over it. But the deepest darkness lies at the beginning of everything. To understand the true nature of these cosmic phantoms, we must journey back over 13 billion years to the era known as the Cosmic Dawn. This was a time before the first stars, a universe plunged in an opaque, primordial fog of hydrogen gas. And here, a terrifying and beautiful theory emerges. The very first galaxies were not born bright. They were born dark. Imagine a newborn universe where vast halos of dark matter, the first structures to condense out of the expanding cosmos, began to pull in enormous clouds of pristine gas. These were the proto-galaxies, colossal wombs of potential, but turning that gas into stars was not an instant process. It required cooling, condensation, and a delicate gravitational dance that could take hundreds of millions of years. For eons, these infant galaxies would have existed as monstrous, swirling spheres of pure, starless gas, held together by their dark matter hearts. They were the ultimate dark galaxies, not because they were failing, but because they were waiting. They were the universe holding its breath before the first scream of light. This primordial darkness is not an absence, it is a pregnant silence, the necessary precursor to all creation. We have glimpsed possible remnants of this epoch in the form of staggering objects like Himiko, a colossal blob of gas detected from when the universe was less than 1 billion years old. Himiko is a behemoth, tens of thousands of light years across, glowing not from starlight but from the energy of infalling gas and perhaps the faint first sparks of stellar birth. It is a cosmic embryo on a galactic scale, a candidate for a dark galaxy caught in the very act of awakening. Surrounding other early luminous galaxies like the brilliantly nicknamed CR7, astronomers find vast dark halos of gas, the unseen fuel reservoirs from which the first stellar cities were built. The fear this inspires is foundational. It means that darkness is not a later stage of galactic life, nor is it a failure. Darkness is the default state of the cosmos. Light is the exception, the hard-won achievement. Every brilliant spiral and elliptical galaxy we see today, including our Milky Way, began its existence as one of these primordial dark phantoms, a ghost that slowly learned how to shine. When the James Webb Space Telescope peers into the deepest fields, it is not just looking for the first lights. It is searching for the last shadows, for those vast, red, gaseous blobs that represent the universe's original dark architecture. We are the descendants of ghosts living in a world built from the ashes of that primordial night. This discrepancy between prediction and reality is not a minor error. It is one of cosmology's most persistent and embarrassing puzzles, known simply as the missing satellite problem. Our most sophisticated supercomputer simulations of cosmic evolution, which model how dark matter clumps together from the Big Bang to the present day, paint a very specific picture of our galactic neighborhood. They predict that the Milky Way's immense dark matter halo should be swarming with thousands of smaller satellite galaxies, gravitational echoes of the early universe. Yet when we look up, we can only confidently identify about 60. So where are the other 9,400? The answer, and the 14th dark galaxy on our list, is not a single object but a terrifying collective. The missing satellites are not missing at all. They are hiding in plain sight as dark galaxies. These are the failed fragments, the cosmic stillbirths our simulations predict but our telescopes cannot see. They possess the mass, the dark matter halos, and the gravitational influence, but they never managed or were prevented from lighting up with a significant population of stars. They are the ghosts in the machine, the invisible majority that haunts every simulation. Visualize a side-by-side comparison. On one screen, a supercomputer render shows the Milky Way surrounded by a vibrant, buzzing cloud of thousands of faint points, each representing a predicted dark matter halo capable of hosting a dwarf galaxy. On the other screen, our actual telescopic view shows our galaxy with only a sparse handful of visible dwarf companions, like the Large and Small Magellanic Clouds. The empty space between them is not empty, it is filled with the unseen. This realization injects a profound fear into cosmology. It means the universe is not just sprinkled with a few dark oddities. It is structurally, fundamentally dark. For every luminous dwarf galaxy we see orbiting a giant like the Milky Way or Andromeda, there could be 10, 20, or even 100 completely dark counterparts. Our local group of galaxies is not a well-lit archipelago in a dark sea. It is a dense, teeming metropolis where most of the buildings have no lights on. Every time we feel we have mapped our cosmic backyard, this problem whispers that we have only charted the street lamps, while entire cities of shadow stretch out between them. The darkness is not an absence, it is the overwhelming majority. This theoretical extreme takes us to the edge of what is possible and perhaps what is real. The 15th dark galaxy is not one we have found, but one we fear must exist. Imagine a dark matter halo that formed in the earliest moments of the universe, a gravitational seed so small, so isolated, or born in such a barren region of space that it never gathered a single wisp of hydrogen gas. No swirling disk of fuel ever coalesced, no protostellar cloud ever collapsed. This structure would evolve over billions of years, growing through mergers with other dark halos, becoming a massive, intricate web of invisible matter, all without ever sparking a single star. It would be a galaxy in every gravitational sense, with a dense core and a sprawling halo, yet it would be composed of 100% dark matter. A perfect cosmic phantom. The fascination with such an object is matched only by the profound fear it inspires, because it represents the ultimate limit of our blindness. We could fly a spaceship directly through the heart of such a galaxy and never know it was there. Our instruments would register nothing, no light to see, no gas to detect, no stellar wind to feel. We would pass through a ghost town built on a scale of hundreds of thousands of light years, utterly unaware of the immense, invisible architecture surrounding us. The only way we could ever hope to detect such a perfect dark galaxy is if it betrayed itself through a cosmic accident. If it drifted precisely between our telescopes and a more distant, bright galaxy, its immense gravity would act as a lens. It would warp and bend the fabric of spacetime itself, distorting the light from that background galaxy into faint arcs or multiple images, a telltale signature called gravitational lensing. We would see a ghost not by its own light, but by the way it twists the light of others. This is the chilling promise and the frustrating hunt. Astronomers meticulously scan the sky for unexplained, isolated gravitational lenses that cannot be attributed to any visible galaxy. Each one is a potential candidate for a pure dark matter galaxy, a shadow caught in the act of bending reality. Finding one would be a monumental discovery, confirming that the universe builds structures we can never truly see, that darkness is not just a component of galaxies, but can be a galaxy unto itself. It would mean the cosmos is filled with these perfect ghosts, silent and eternal, shaping the universe from the shadows without ever once revealing their form. Even now, a ghost is on a collision course with our home. Racing toward the Milky Way's disk at over 200 miles per second is a colossal, dark structure known as the Smith Cloud. Stretching over 10,000 light-years long, this is no wispy tendril of gas. It is a monstrous river of cold hydrogen, carrying enough raw material to forge 2 million stars the size of our Sun. Yet it emits no light of its own. For decades, it was catalogued simply as a high-velocity cloud, an anonymous blob of intergalactic fuel. But its trajectory tells a far more sinister story. This cloud is not just passing by, it is hurtling directly toward the outer spiral arm of our galaxy, due to strike in roughly 30 million years. The question that haunts astronomers is a simple one: what is it? One possibility is that the Smith cloud is the tattered remains of a dark galaxy being cannibalized. Imagine a small, failed dwarf galaxy, all but devoid of stars, that ventured too close to the Milky Way eons ago. Our galaxy's immense gravity could have reached out and begun to unravel it, stretching its gaseous body into this long, streaming ribbon we see today. The cloud's intricate filamentary structure and the presence of heavier elements like sulfur suggest it was not born in the pristine void between galaxies, but was enriched by stellar processes long ago, hinting at a past where stars did indeed shine within it. This would make it a galactic ghost in its final death throes, its identity all but erased, leaving only its dissipating corpse to crash into our own. But there is a second, more unsettling theory. Perhaps the Smith cloud is not a galaxy at all, but something else entirely. Recent observations suggest it is wrapped in a cocoon of hot, ionized gas, a protective sheath that might be holding the cold core together. This could indicate it is a massive gas cloud ejected from the outer regions of the Milky Way itself, perhaps by a series of powerful supernova explosions billions of years ago, now falling back home in a great cosmic boomerang effect. The fear embedded in this mystery is twofold. First, we cannot see what is pulling the strings. The cloud's motion suggests it is being guided or even dragged by an immense mass. Is that mass the invisible dark matter halo of a disintegrated dwarf galaxy, a ghostly hand still steering its remains, or is it simply the Milky Way's own gravitational pull? We do not know. Second, and more viscerally, we are forced to confront the inevitable future. In 30 million years, this colossal spear of hydrogen will slam into the galactic plane. The impact will be less like a bullet and more like a tsunami. As the cloud plows into the denser gas of our galaxy's disk, it will trigger a shockwave of unimaginable scale, compressing gas clouds across a vast region and igniting a firestorm of star formation. An entire sector of the Milky Way will light up with the blue blaze of millions of newborn stars, a spectacular but violent celestial fireworks display. The Smith cloud is a reminder that our galaxy is not a static island. It is a dynamic, hungry entity still gathering its building blocks from the darkness. Whether it is the last gasp of a dark galaxy or a returning exile, it is a herald of a future cataclysm, a dark messenger announcing that even the Milky Way's evolution is written in collisions with the unseen. Its delicate nature makes it a cosmic paradox, a ghost that refuses to fade completely. Leo T is a dwarf galaxy so faint it dances on the very edge of detectability, a smudge of light over 700,000 light-years away. But within its fragile form lies a startling contradiction, a dual personality that defies the simple story of galactic life and death. On one hand, Leo T is ancient. The majority of its stars are old, red, and metal-poor, relics from the early universe that have burned quietly for billions of years. This is the hallmark of a dormant galaxy, one whose star-forming days are long over. Yet, nestled among these ancient embers, astronomers have found the unmistakable, brilliant blue spark of young stars, not just a few, but a small, ongoing nursery. Even more telling, Leo T is one of the smallest and faintest galaxies known to still possess a significant reservoir of cold, neutral hydrogen gas, the raw fuel for making new suns. This is like finding a tiny, flickering candle that not only refuses to go out but occasionally flares with a fresh, new flame, all while sitting in a vast, cold room. The intrigue here is not about overwhelming darkness but about delicate, stubborn light. How can something so small and faint possibly keep the fires burning? The answer, as with so many of these phantoms, points to the unseen. Despite its wispy appearance, Leo T is not lightweight. Measurements of the motions of its stars reveal it is held together by a massive, invisible anchor. Its dark matter content is immense for its size, meaning this faint celestial firefly is actually encased in a heavy, protective shell of mystery matter. This dark matter halo may be the key to its survival, providing just enough gravitational pull to retain its precious gas against the evaporating effects of intergalactic space and the Milky Way's own subtle pull. But the fear is about fragility. Leo T exists in a precarious balance. It is a miniature, closed ecosystem in a hostile cosmos. A single close encounter with another galaxy, or even a strong burst of radiation from a nearby event, could easily strip away its tenuous gas, snuffing out its star formation forever and relegating it to the realm of the completely dormant. The fact that it still flickers with new life suggests it has lived an incredibly sheltered, isolated existence, a hermit galaxy that has avoided the violent gravitational dramas that have shaped its larger cousins. This makes it a precious time capsule. Leo T is not a failed giant or a shredded remnant. It is a pristine example of a small galaxy that has, against all odds, persisted. Its ongoing, feeble star formation is a whisper from a much earlier era of the universe, a process that has somehow continued in slow motion. Studying it is like watching a single, persistent ember glow in a fireplace long after the main fire has died, a testament to the stubborn, delicate will of the cosmos to create, even in the faintest of forms. Our own galactic backyard holds a resident so faint it defies simple classification. This is Willman 1, a smudge of light discovered just outside the Milky Way's disk, an object caught in a profound identity crisis. To our most powerful telescopes, it appears as nothing more than a sparse, fuzzy collection of a few hundred ancient stars. At first glance, it looks almost identical to a globular cluster, one of those dense, spherical balls of stars that orbit galaxies like loyal, ancient sentinels. But looks, especially across cosmic distances, can be a terrifyingly deceptive thing. The central question that has divided astronomers for years is deceptively simple. Is Willman 1 a star cluster, or is it a galaxy? The answer is not just academic trivia. It is a key that unlocks two completely different histories and instills a deep fear about the limits of our perception. If Willman 1 is a globular cluster, then its story is straightforward. It would be a structure born from the gas of a larger galaxy, likely our own Milky Way, condensing into a tight, gravity-bound sphere of stars with little to no dark matter of its own. Its mass would be simply the sum of the stars we see, but if it is a dwarf galaxy, everything changes. A dwarf galaxy forms independently from its own primordial cloud of dark matter. It would be embedded in a massive, invisible halo, meaning its true weight is dozens or even hundreds of times greater than its visible light suggests. The same faint smudge of light would represent two cosmic objects of vastly different scales and origins. The evidence is maddeningly ambiguous. Its stars are spread out more diffusely than a typical globular cluster, hinting at the weaker gravity you would expect if it were mostly dark matter. Yet, it is not as extended as some confirmed dwarf galaxies. Our tools strain at the limit of their resolution, unable to deliver a definitive verdict. This ambiguity is the true source of fear. It means there could be hundreds, even thousands, of objects like Willman 1 sprinkled around the Milky Way, each a cosmic Rorschach test. Are we looking at simple star clusters or the dense, star-poor cores of failed dark galaxies? Our current census of the Milky Way's satellites, the 60 or so we have found, might be missing an entire hidden population of these borderline phantoms. Every time we point our telescopes at a faint, fuzzy patch, we must now ask a haunting question. Are we seeing a family of stars, or are we seeing the last surviving evidence of a dark matter fortress that never truly ignited? The universe, it seems, delights in hiding its most fundamental structures in the blurry space between our categories. Hercules is a ghost being stretched on a cosmic rack. This ultra-faint dwarf galaxy, one of the Milky Way's most elusive satellites, is not simply orbiting our home. It is being slowly, meticulously torn apart by it. Hercules is so dim that its total light output is less than that of a single bright star in our own galaxy, yet it sprawls across a vast region of space. This extreme faintness combined with its stretched, elongated shape tells a terrifying story of gravitational torture. The Milky Way's immense tidal forces are pulling at Hercules, drawing its stars out into long, faint streams that precede and trail its orbit like celestial cobwebs. We are witnessing a galaxy in its death throes, a real-time, slow-motion tragedy unfolding over billions of years. The numbers reveal the violence. Hercules possesses a mass-to-light ratio that is staggering, meaning for the tiny amount of light it emits, it holds an enormous amount of mass, most of it dark and invisible. This dark matter halo is the galaxy's skeleton, and even that is now being distorted. Visualize a time-lapse spanning eons. A small, compact sphere of stars enters the frame, drifting toward the glowing disk of the Milky Way. As it swings close on a long, elliptical orbit, the galaxy's gravity takes hold. The near side of Hercules feels a stronger pull than the far side, and with each pass, this difference stretches the dwarf. It begins to elongate, its stars pulled away from the main body, first into a teardrop shape, then into a long, thin filament that eventually wraps around the Milky Way in a dissolving ring. Hercules is currently in the teardrop phase, a snapshot of cosmic disintegration. The fear it embodies is visceral, it is the fear of inevitability. This is not a theoretical model or a computer simulation, it is an observation of a galaxy actively being destroyed. Its stretched form is a fossil record of its own execution, written in the positions and motions of its remaining stars. Every ultra-faint dwarf we discover, we must now examine for similar distortions, wondering if we are seeing a stable object or one already caught in the fatal grip of a giant. Hercules teaches us that the quietest ghosts often have the most violent stories, their faint whispers describing a final, drawn-out scream against the overwhelming pull of darkness. Just beyond the reach of Hercules lies a pair of siblings so faint they seem to dissolve into the void itself. Bootes 1 and Bootes 2 are ultra-faint dwarf galaxies, the closest known examples of this ghostly class, drifting within our own galactic halo. If you could stand on a world inside Bootes 1, the night sky would be a profound and terrifying emptiness. You would see only a few dozen stars in your entire sky, each one ancient and lonely, separated by gulfs of darkness so vast you could mistake them for distant islands in an endless black sea. These are not collections of stars so much as they are suggestions of stars, the faintest possible proof that a galaxy could exist at all. Their light is so meager that it took the most sensitive digital sky surveys to pluck their signal from the background noise of the Milky Way, like hearing a single whisper in a roaring stadium. This extreme faintness is not a sign of small mass, however. Measurements of the motions of those scant stars reveal they are moving with a surprising speed, held in orbit by the gravity of an immense unseen anchor. Bootes 1 and 2, like so many of these phantoms, are utterly dominated by dark matter. For every single photon of light we detect, there are thousands of solar masses of invisible matter holding the entire structure together. They are dark matter halos that, almost as an afterthought, contain a handful of ancient stellar embers. The fear they represent is not about their individual strangeness, but about what they imply for the cosmic census. Bootes 1 and 2 are not oddities, they are pioneers. They exist at the very bleeding edge of our detection capabilities. Their discovery proved that galaxies could form and persist with such miserly starlight that they nearly fade into the cosmic background. This leads to a chilling and inevitable question. If these are the faintest galaxies we can see, how many more are just below that threshold? Our current telescopes have a flaw, a limit of sensitivity. What if, just beyond that limit, there exists a vast, hidden population of even darker, even more diffuse galaxies? Bootes 1 and 2 are like the first few pebbles you notice at the water's edge, but they hint at an entire beach buried beneath the surf, a shadowy archipelago of failed galaxies orbiting our own, each one a near-perfect phantom. They represent the lowest possible end of the galaxy formation scale, and their existence suggests that the true number of satellites swarming the Milky Way could be in the thousands, not the mere dozens we have catalogued. Every time we build a more powerful telescope, we push that detection floor a little deeper, and every time we find more of these ghosts, the darkness, it seems, has no bottom. The faintest dwarfs are whispers, but the largest galaxies in the universe broadcast their history in a different kind of dark halo. The 21st dark galaxy is not a single object, but a vast, silent shroud enveloping the universe's brightest giants. Look at a massive elliptical galaxy like the famous M87 at the heart of the Virgo cluster. In a standard telescope image, it is a brilliant, smooth egg of light, a city of trillions of ancient stars. But when astronomers use special processing techniques to subtract that overwhelming glare, a terrifying truth emerges. The galaxy is not an island, it is the glowing core of something far larger and darker. Extending for hundreds of thousands of light years beyond the visible edge is an immense ghostly halo of dim, old stars and overwhelmingly dark matter. This is the cumulative debris of a monstrous appetite. A giant elliptical galaxy like M87 did not form peacefully. It is the product of 1,000 mergers, a cosmic cannibal that has devoured countless smaller galaxies over billions of years. Each time a spiral or dwarf galaxy was drawn in and shredded, its stars were not all absorbed into the bright core. Many were flung out into chaotic, distant orbits, forming this vast, diffuse cloud. Its dark matter halos merged into an even larger, invisible gravitational fortress. This faint stellar halo is a galactic graveyard, the silent aftermath of a violent history. The fear it embodies is one of scale and finality. We are looking at the quiet end of cosmic evolution. All the drama of colliding spirals, of star-forming bursts and tidal tails, culminates in this, a bright, quiet core surrounded by an ocean of dark, settled ruins. The most luminous galaxies in the universe are, in fact, the centers of the darkest regions, anchored by halos of unimaginable mass accumulated from countless victims. This transforms our view of these cosmic giants. They are not just collections of stars, they are tombs. Their faint, extended halos are the fossil records of entire galactic ecosystems that have been consumed and assimilated. And if this is true for the brilliant ellipticals at the heart of clusters, it is likely true for galaxies like our own Milky Way on a smaller scale. We too may be surrounded by a vast, dark shroud of stellar and dark matter debris, the remnants of smaller galaxies we have digested over the eons. The brightest lights in the cosmos are forever ringed by the ghosts of their past, a permanent memorial to the violence that built them. But the influence of the dark may reach far beyond the halos of individual galaxies. There is a controversial observation so unsettling it suggests the entire visible cosmos is caught in a current flowing toward an unseen shore. This is the phenomenon known as the dark flow. When scientists meticulously mapped the motion of thousands of massive galaxy clusters, they found something that defied all conventional models. After accounting for the uniform expansion of the universe, these titanic structures showed a persistent residual velocity, all streaming in the same direction. It was as if an immense, invisible hand was tugging on the fabric of the cosmos, pulling everything toward a single point on the edge of, or even beyond, our observable horizon. The implication is a fear that redefines scale. What gravitational force could possibly move entire clusters of galaxies, each containing thousands of galaxies themselves? The terrifying answer points to structures of such staggering size and mass that they exist outside our cosmic view. Imagine our entire observable universe, a sphere nearly 100 billion light-years across, not as the totality of existence, but as a single island in a far vaster ocean. The dark flow, if real, would be the gravitational tide from a neighboring island so colossal it drags our entire island through the sea of spacetime. These would be dark megastructures, agglomerations of matter and dark matter on scales that dwarf superclusters. realms so immense they exert a gravitational pull across the void that separates cosmic horizons. Visualize an animation of our observable universe as a glowing bubble, arrows representing thousands of galaxy clusters all slowly, inexorably, point toward one sector of the bubble's edge, as if the bubble itself is drifting in a hidden river. This is not just a hidden galaxy, it is a hidden architecture of reality, a dark framework so vast it makes our entire cosmic neighborhood feel like a speck of dust in a hurricane. The scientific community remains deeply divided on the dark flow, with many attributing the signal to measurement errors or subtle astrophysical effects we do not yet understand. But the mere possibility chills the spine. It forces us to confront the ultimate limit of our knowledge, the horizon beyond which we cannot see, and to wonder what unimaginable giants might be lurking there, their silent gravity steering the course of everything we know. These cosmic phantoms are more than just celestial oddities. They are the universe's own built-in laboratories. Each dark galaxy, from the ghostly wisp of Segway 1 to the stretched skeleton of Hercules, offers a pristine, controlled environment to study the one ingredient we cannot see, dark matter itself. In a normal, bright galaxy, the violent astrophysical processes of star birth and death, supernova explosions, and swirling magnetic fields create a chaotic background noise. It is like trying to hear a whisper in the middle of a roaring concert, but a dark galaxy, especially one with almost no gas and ancient, quiet stars, is a silent, sterile chamber. The only force at play in these vast, empty spaces is gravity, and the only source of that gravity is the dark matter. This allows scientists to map its distribution with incredible precision, to weigh it, and to test how it behaves under conditions we could never recreate on Earth. The fear embedded in this research is not of the galaxies, but of the answers they might provide. Every observation is a test of our fundamental theories. For instance, the way dark matter is distributed in a galaxy's halo can tell us if it is cold, meaning its particles move slowly and clump easily, or warm, moving faster and forming smoother, less concentrated halos. The stark dominance of dark matter in objects like Dragonfly 44 strongly supports the cold dark matter model, the backbone of our cosmic simulations. Yet, the apparent lack of dark matter in galaxies like NGC 1052DF2 throws a wrench into that machinery, suggesting either a bizarre formation history or a need to revise our understanding of gravity itself. Each dark galaxy is an experiment already running, and we are just collecting the data. The most profound tests involve the nature of the particles themselves. Within the silent hearts of these dark laboratories, scientists hope to catch dark matter in the act. One leading candidate is the WIMP, the weakly interacting massive particle. In a dense dark matter halo, these theoretical particles could occasionally collide and annihilate each other, producing a faint spray of gamma rays, exactly the kind of signal we might be seeing from Triangulum 2. Another candidate is the Action, an extremely lightweight particle that, in the presence of a strong magnetic field, could theoretically convert into a faint radio whisper. A dark galaxy, with its immense dark matter core and lack of competing radio noise, would be the perfect place to listen for that whisper. Visualize an animation not of stars but of a galaxy's invisible dark matter halo. Within that swirling cloud, two tiny specks labeled as WIMP drift toward each other, collide, and vanish in a flash of gamma-ray light. In another halo, waves labeled as Actions ripple through the darkness, transforming into a subtle radio signal that stretches toward a waiting telescope. What we learn from these dark matter laboratories could do more than solve a puzzle. It could tear down our current map of reality. The standard model of particle physics, which brilliantly explains every particle and force we have ever detected in accelerators, is utterly silent on dark matter. It does not have a place for it. A confirmed detection of a WIMP or an Action would be the first crack in that model, the first undeniable proof of a whole new physics operating at scales and energies we have never probed. The universe might be far darker and more complex than our elegant equations suggest, built from substances that interact with our world only through the faintest gravitational touch. The fear, then, is the fear of obsolescence. We may be on the verge of discovering that the luminous universe we have spent centuries studying is merely the decorative frosting on a cake made of something entirely alien and unknown. Every dark galaxy we study is a window into that deeper, darker layer of existence, and each observation brings us closer to a revelation that could rewrite the textbooks of physics forever. The next leap in our vision will come from a telescope named for a pioneer. The Nancy Grace Roman Space Telescope, set to launch later this decade, will not look at a single point in the sky, but will conduct a panoramic, high-resolution survey of enormous swaths of the cosmos. Its mission is to stare wide, not just deep, mapping the universe with a field of view 100 times larger than the Hubble Space Telescopes. For the hunt for dark galaxies, this is a game-changer. Roman will scan vast stretches of emptiness where our current telescopes see nothing, systematically searching for the ultra-faint, diffuse smudges that have eluded us. It is designed to find the ghosts hiding in the crowd, the phantoms we have missed because we were looking through a keyhole. Imagine a dark room where you have only been able to shine a narrow, powerful flashlight, illuminating a few strange objects. Now someone flips a switch and the overhead lights come on, revealing that the room is not empty at all, but filled with hundreds of faint, shadowy shapes. That is the promise of Roman. It could reveal a hidden population of dark galaxies so vast it would confirm our darkest suspicions that the luminous universe is merely the tip of a gargantuan, invisible iceberg. The simultaneous fear and excitement is palpable. On one hand, finding thousands of these objects would be a triumph, finally solving the missing satellite problem and proving our models of dark matter correct in their predictions. On the other, it would force a humbling realization that most of the structures in the cosmos are, and always will be, completely invisible to our eyes. But the James Webb Space Telescope offers a different, complementary power. While Roman stares wide, Webb stares deep with an unprecedented sensitivity to infrared light. This allows it to peer back to the cosmic dawn, to see the earliest galaxies not as they are today, but as they were when the universe was in its infancy. Webb is hunting for the primordial dark galaxies, those colossal, gaseous wombs that existed before widespread starlight. It is looking for the red, bloated shapes of himiko-like objects, the dark embryos from which all modern galaxies were born. The combined power of these observatories is our greatest hope and our greatest anxiety. They represent a fundamental test. If they find the legions of dark dwarfs and the first dark giants that our theories predict, we will have mapped the true, shadowy skeleton of the cosmos. But what if they do not? What if, after all this technological marvel, after Roman's wide gaze and Webb's deep vision, the sky remains stubbornly empty of these phantoms? That outcome is, in many ways, more terrifying. It would mean our most cherished cosmological models, the very frameworks we have used to understand the universe for decades, are fundamentally flawed. The missing satellites would remain missing not because they are dark, but because they never existed in the first place. We would be forced back to the drawing board, confronting a universe where dark matter behaves in ways we never predicted, or where our understanding of gravity itself is incomplete. The data streams from these telescopes will not just bring answers, they will bring a crisis, a beautiful, necessary crisis that will either solidify our cosmic map or force us to burn it and start anew. We are poised on the edge of a revelation, waiting for the universe to show us whether the darkness is a populated realm of ghosts or a deeper, more profound silence than we ever dared to fear. The final and most profound fear is not about any single galaxy, but about the nature of reality itself. We have journeyed through a catalogue of cosmic phantoms, from the failed and the shredded to the ancient and the annihilating. Each one, from Dragonfly 44 to the faint whispers of the Boots dwarfs, chips away at our assumption that the universe is a place of light. The accumulating evidence points to a terrifyingly simple conclusion. Dark galaxies are not rare anomalies, they are likely the rule. For every brilliant spiral like our Milky Way, there could be dozens, even hundreds of these invisible halos, these silent structures that contain the mass but not the light. This inverts our entire cosmic perspective. We have spent centuries marveling at the glittering cities of stars, mapping the luminous architecture of the cosmos and believing that was the universe. But what if we have only been studying the streetlights? What if the true structure, the massive framework, the continents and mountain ranges of the cosmos are built from a material we cannot see, touch, or truly comprehend? Our beautiful, star-filled galaxy may not be a typical citizen of the universe. It could be a rare overachiever, a brilliant exception in a cosmos dominated by darkness and silence. This is an existential shift. It means that most of the universe's matter, and therefore most of its gravitational influence, its shape, its very skeleton, exists in a form that is forever hidden from our senses. We are living in a ghost town, surrounded by invisible buildings whose presence we can only infer by the way they bend the space around us. The final shot is not of a single dark galaxy, but of the cosmos at its grandest scale. Picture a simulation of the entire observable universe, not as a web of shining galaxies, but as a web of shadow. Billions of faint, translucent halos of dark matter stretch across the void, connecting in a vast, intricate cosmic web. And within that web, like tiny, brilliant Christmas lights strung far apart on an endless black cable, are the pinpricks of luminous galaxies. They are the decoration. The darkness is the structure. This is the ultimate fear, that we are not at the center of a bright and knowable universe, but are temporary residents in a realm whose true nature is, and may always remain, shrouded in night. Our quest to understand the cosmos has led us to a humbling frontier, where the greatest discovery is the sheer, overwhelming scale of what we do not see. Our journey through the shadows has revealed a cosmos far stranger than we ever dreamed. We have seen the ghostly Leviathan Dragonfly 44, a galaxy of almost pure dark matter, and the perplexing void of NGC 1052 DF2, which seemed to defy the need for dark matter entirely. We witnessed the silent suicide in Triangulum 2, the stretched agony of Hercules, and the stubborn, flickering life within Leo T. From the primordial dark embryos of the cosmic dawn to the dark flow that may tug at our entire horizon, each of these 25 phantoms represents a crack in our understanding. They are not just celestial oddities, they are the universe's way of asking questions we are only beginning to phrase. They challenge our fundamental ideas about what a galaxy is, how gravity works, and what truly holds the cosmos together. They force us to admit that most of the universe is built from a substance we cannot see, in forms we are only starting to map. This is the frontier of our ignorance, a vast and dark territory where every new discovery overturns an old assumption. Yet, this fear of the unknown is not a dead end. It is the very engine of discovery. By daring to look into the darkness, by fearing these cosmic ghosts enough to study them, we are not admitting defeat. We are turning on a light. Each observation, each puzzling signal, each faint smudge of light in the void is a beacon guiding us toward a deeper truth. The dark galaxies are the universe's greatest puzzles, and in solving them, we may finally understand the hidden architecture of reality itself, an architecture built not from light but from a profound and beautiful darkness. Tell us in the comments which of these dark galaxies chilled you to the core. Was it the perfect phantom Segway one or the doomed trajectory of the Smith cloud? Share your thoughts and subscribe for more journeys into the deepest mysteries of the cosmos.